Good morning. In this lecture, I will discuss off-diagonal long-range order and the connection of that with spontaneously broken continuous symmetry in Bose systems. Um, so let's start with the definition of Bose-Einstein condensation that you know, which essentially involves macroscopic occupation of a single quantum state. And typically, we deal with large systems with periodic boundary conditions. So that single quantum state becomes the k equal to 0 state. But it could also be a harmonic trap, as people are able to create with cold atomic gases. In this case, you have discrete levels due to the quantization, and the macroscopic occupation now can happen, for example, in the n equal to 0 state. Okay, we would like to go beyond this definition to understand it more deeply. Now, going with what we learned in magnetism, we saw that if you look at order parameters that are vector-like, for example, with O2 symmetry lying in the xy plane, or with O3 symmetry lying in three-dimensional spin space, then you have to look at a spin-spin correlation at two different positions, r and r prime. And these are vectors, so you look at the dot product. And if you make r and r prime large and well separated, this correlation function factorizes into individual expectation values of the spin operator at site r, dotted with the spin at site r prime. If this is non-zero, we say that the system has long-range order, because that's precisely what this is showing, that the spin at some site r prime has uh, uh, is correlated with the spin at a distant location r. And this allows us to define a local order parameter, which is the expectation value of S at r. And this is a vector m. Now, this local order parameter, when in the high temperature phase, it points in a random direction, so the expectation value is 0. So you can see that its expectation value can be 0 due to two reasons. One is the magnitude can be 0, and the other is that it can point in arbitrary directions. So if you average over all of these directions, you get 0. At low temperatures, the system spontaneously breaks this rotational invariance in spin space by picking one specific direction. And that is what we call broken symmetry. As we saw, this broken symmetry can be discrete in nature, as in the Ising model, or continuous, as in the XY or Heisenberg O3 models. And the reason we use the word spontaneous is because when we go from the high temperature to the low temperature phase, we are not explicitly breaking this symmetry by adding an external magnetic field that couples to the order parameter. Just by virtue of taking the thermodynamic limit of the possible ground state minima the system could exist in, the system picks one of them spontaneously. Another way to think about it is you can apply a small symmetry breaking field, cool the system, and then take the limit h going to 0. But even in the absence of that, typically because of random fluctuations, the system will break this symmetry spontaneously. Okay, so the main question we want to ask in this lecture today is, what are the analogous quantities for Bose condensed systems? And there, the early work was done by Penrose and Onsager and C.N. Yang, and they introduced the one particle reduced density matrix rho between the states R and R prime. And that's defined by the creation operator at R prime destruction operator at R, and the expectation value of this combined operator. It's important to note that this definition is also valid when temperature is not zero, in which case, rather than take its expectation value in a particular state, the ground state, you can do a thermal expectation. Okay, so let's write it out by Fourier transforming these operators. So we have psi dagger, which is the Fourier transform of a k dagger, and psi, the Fourier transform of a k. And when you write it out, what you get is the expectation value of a k dagger a k, which is the number operator for counting the number of bosons in state k. And that essentially is the momentum distribution function after you take the average. So this expectation value that we are interested in, which tells us about long range order, is essentially the Fourier transform of n of k, the momentum distribution function. Now, if the system is a BEC, meaning that there is an expectation value which is non-zero when these operators are separated by large distances, that implies that n of k has this structure. There is a singular piece with weight at momentum k equal to 0. That is the condensate number n0 plus a less singular piece n of k, n tilde of k. And what we see is that this implies that our psi dagger psi at two different positions, its expectation value at large distances goes to n0 divided by omega, and n0 is the number in the zero momentum state. So this ratio is just the condensate density. And off-diagonal long-range order then essentially implies that this expectation value is finite at large distances. Conversely, in a system that does not show a BEC, this correlation function must go to 0, and that can occur under two situations. One is it exponentially decays to 0. That implies that that state is a normal liquid. On the other hand, if it decays to 0 as a power law, then that can happen either at a critical point, or if it's in 2D, then it can occur through the BKT mechanism, the Kosterlitz-Thouless mechanism, in Bose systems such as helium-4 films, in spin systems in the XY model, as well as in 2D superconducting films. It can also occur in quantum phase transitions in 1+1D systems because they map into effectively 2D classical systems. Okay, next we want to delve a little bit deeper to understand the meaning of this long-range correlations. So going back to the magnetic analog, we saw that when you look at two spin operators at distant points, and that expectation value at large separation basically becomes a product of the individual expectation values. So it factorizes. The question is, can we write the bosonic problem, psi dagger psi, also when separated over large distances, as a product of the average of psi dagger times the average of psi? And what does this mean? Now, if you have a ground state with a fixed number of bosons, n, then we can see that this expectation value, writing it out more explicitly, psi dagger, its expectation value in these fixed number states has to be 0. So does this mean that if you have a system with a fixed number of particles, then it cannot have off-diagonal long-range order? And the answer to this is no. So how can it possibly be that you have a fixed number of particles, and yet I'm saying that the system does have ODLRO? So we need a more sophisticated understanding of this expectation value of psi dagger, and that is what I'm going to discuss next. Obviously, it cannot be that you take this expectation value in fixed number states, but then how do you understand such an expectation value if your system indeed has a fixed number of particles? So the way to understand this is to take a macroscopic system, a very large system of volume omega, and to break it up into, and let's say this very large system has a fixed number of particles n. But now let's break it up into small subsystems. And each of these subsystems itself is macroscopic. And so we have a large number m of these macroscopic subsystems that I'm going to label by I, which goes from 1 through m. And in this big system, I'm going to write my boson creation and destruction operators as AK dagger, AK, with the capital A's. So in the large system, A0 dagger A0 is equal to N0. That because I'm saying that in the large system, I have a BEC. I'm going to start with that assumption. The question is to understand what is the meaning of psi dagger average. Where is this average being taken? Okay, so what I will do next is to look at the behavior in the little subsystems and then try to correlate what is happening within a subsystem and between subsystems. And therein will lie the answer to this question that I have raised. So let little AI0 dagger be the creation operator in the subsystem I, that's the first label, and it creates a particle in the k equal to 0 state in the subsystem I. Okay, so capital A0 dagger then is just a sum over these little AI0 daggers summed over all I, all the subsystems, with a 1 over square root m factor. And similarly for A0. You should check that this 1 over square root m factor is absolutely required. It is mandated by the Bose commutation relations that both big A and little a must satisfy. So N0 now is equal to A0 dagger A0. That's the definition we started with if you have a BEC in the full system. And that can be written as a sum by substituting for A0 dagger and A0 from here. It can be written as one term that captures the operators within a subsystem, and a second term that captures what the operators are doing, creating and destroying bosons in two different subsystems, always in the k equal to 0 state in all of these terms. Now, what you get now is that N0, which is macroscopic, it's of order n, total number of particles, is equal to N0 over m. That's the number in the subsystem, in any of the subsystems over m, that's the number within that. And this, you could see, is tiny compared to the left-hand side because m itself is very large. And then there's a second term, which involves these correlators in two different subsystems. And so clearly, if the right-hand side has to equal the left-hand side and the first term is tiny, most of the contribution has to come from these correlators of the creation and annihilation operators in very different subsystems. But that term has to be of order m times n, so that the m term gets cancelled by the prefactor, and you're left with a term of order big N. So what have we learned? What we are seeing is that in order to get a BEC in the full subsystem, you require not only a BEC in each macroscopic subsystem, but you also require that there be strong correlations between distant macroscopic subvolumes. Okay, so that is where we have taken the discussion now. We still need to understand in now what exactly are these strong correlations between distant subvolumes. And that becomes more clear if we define the expectation value of the operator psi or psi dagger as square root of n0 e to the I theta. So it's a complex number with a magnitude which is n0 and given by capital N0 over omega times a phase factor e to the I theta. And note here, theta is independent of r. So if we want to understand, if we start with such a definition, where does it take us? And how does it deepen our understanding of this long range correlation that is needed for the full system, the full big system, to have a BEC? Okay, so let's look at the creation operator in the ith cell that creates a boson with momentum k equal to 0 and Fourier transform it in terms of, sorry, this should be a psi dagger. Fourier transform, this is basically an average over psi dagger Ri at Ri, where Ri is integrated over the ith cell. And now for the whole system, we can now write down A0 dagger A0. Average is basically these cell operators in each subvolume. And we can write that in terms of these bosonic operators, psi, the very local operators, psi, and A is averaged over the cell. Okay, so we are kind of coarse graining over a cell. And you can see that if you write it out, what you get is the first prefactor is 1 over m. From the sum over I and j, you get a factor of m square. From the integral over dri drj, you get omega over m whole square. And now what I have done is here I had the product of these two operators. And let's say at large distances, this basically becomes this separate averages, as we have been talking about. That's the signature of a BEC. What would it imply if we chose such a definition for the average of psi of r? That's what we are trying to understand. We are starting with this definition, and we are trying to understand what is the implication of having such a definition for this long-range correlation. So you can see each of these averages gives you n0 over omega square root, that's the amplitude, and a phase e to the minus I theta from the psi dagger term, and a similar term from the average of psi, except here now you get a e to the plus I theta. So if you look at all of these factors, you see that what is crucial in obtaining A0 dagger A0 expectation value to be N0 is the cancellation of the phases at two different points, distant points. And this cancellation occurs because theta at R and theta at R prime are identical. And because theta is independent of R, as I have written. So what you see is that in order to get A0 dagger A0 to be non-zero, what is required was not just that you had an N0 within each cell, but that there was long-range phase coherence of the bosonic BEC within each cell. That phase was correlated with the phase at distant points. Only then theta at r would be independent of theta at r prime, and they would cancel out to give you this long-range phase coherence. Okay, so we've made some progress. We've understood what is the meaning of psi dagger r psi r prime at average of this, and we have understood that for this to be non-zero, it requires long-range phase coherence. Let's come back to the question we raised, which was the expectation value of psi when it is non-zero. What is the meaning of that? And how can we understand that if our state cannot be a number state? So obviously in a number state, the expectation value is zero. So what I want to now emphasize and kind of get across two main things, and we have already said it, but I want to kind of give it some mathematical structure. And that is, we need two new ideas which would help us understand how the expectation value of psi can be non-zero. The first is, we need a macroscopic cell within the big volume. So the subvolume itself is macroscopic. Even if the number in the total system is fixed, the subvolume is an open system in which n is not fixed within the cell. So we have a grand canonical ensemble for each of these cells where the number of particles is able to fluctuate. But I want to emphasize that that is not enough. We also need to use a coherent superposition of states with different number of particles. And so we write down the ground state as a phi zero of theta. It has a fixed theta as a sum over states with different number of particles, phi zero n, that you add up with this phase e to the I n theta. It's like Fourier transforming between position and momentum. And now we are using number and phase. Okay, so Cn is real and peaked about some average n bar. As we know, we can pick such a representation like the coherent states for bosons. But the other crucial factor is that these different states, phi 0 n and phi 0 n minus 1, occur with a very definite phase relationship between them. So what we get is, if I now take the expectation value of psi in these fixed theta states, phi 0 theta, psi, phi 0 theta, then what you get is a sum over n and n prime, Cn prime, e to the I n minus n prime times theta, and then the expectation value of, or rather this matrix element of psi between two states with differing numbers n and n prime. And since psi acting on a system with n particles gives you square root of n and n minus 1 here, you will get a delta function of n comma n minus 1. Okay, and so what you get is this difference between n and n prime is just 1. So what you get is some amplitude factor f that scales like n bar square root and a phase factor e to the I theta. So that is then, that completes the story, that and it gives us a deep understanding that when we look at the order parameter for a Bose system, which is psi expectation value at any site, you can think of it as a vector. You can think of it like, if this is my space, x and y, you can think of it at any point r, what you have is a vector with some angle, theta. But if you go far away to some other point, let's say this is r prime, the angle there is also theta. And that is the long range phase coherence we have been talking about. So the crucial thing is that this expectation value is taken in states with a fixed theta. And since fixed theta requires a linear superposition of states with different numbers of particles, with this very definite phase relationship between them, we are able to get long-range phase coherence. Okay, so symmetry breaking now becomes the acquiring of a unique phase in the entire system. And as I've emphasized, that unique phase is the same across all points in the system. And that's what we mean by off-diagonal long-range order or long-range phase coherence. So let me summarize now some of the key ideas and that we have been discussing in magnets, and now we have extended it to Bose systems, and let me also contrast it with crystals. So let's look at a few attributes. The disordered state in a Bose system is just the normal liquid or a gas. In a magnet, it's the paramagnetic state, where all the spins are uncorrelated. In a crystal, it's a liquid or a gas. The ordered state in a Bose system is the Bose-Einstein condensate. In a magnet, it's a ferromagnet or an antiferromagnet. And in a solid, it's a crystal, an ordered array of atoms. The broken symmetry in a Bose system is the breaking of phase rotational invariance. In a magnet, it's the breaking of spin rotational invariance. And in a crystal, it's the breaking of continuous translational invariance. Associated with the breaking of a continuous symmetry is the development of a Goldstone mode or a gapless low energy dispersing mode. And in the Bose system, it's a phonon. In a magnet, it's a magnon or a spin wave. And in crystals, it's what is also called a phonon. And these are the elastic modulations. In the Bose system, the phonon is the modulations of the phase. And here it's the elastic modulations. Now, there's a rigidity to creating these modulations of the phase, and that is measured by a quantity called the superfluid density or the phase rigidity or the superfluid stiffness. In the spin case, it's called the spin rigidity or a spin stiffness, and in a crystal or a solid, it's the shear modulus. So like the compressibility is like a longitudinal expansion or compression, and this is a shear, which is a transverse response. Associated with the broken symmetry are topological defects. In the Bose system, these are vortices. In the spin system, depending on the nature of the broken symmetry, you can get domain walls, vortices, or hedgehogs. And in crystals, these are dislocations. So I think this completes a very important concept of what it entails to have a complex order parameter and how you can get correlations of this complex order parameter across the whole system that leads to long-range phase coherence. And ultimately, we are able to define a local order parameter for a Bose system by the expectation value of the creation or the annihilation operator taken in between states that have a fixed phase. And these fixed phase states can be expanded as linear combinations of number states that have a particular relationship between the different number states. Okay, thank you.